Okay, this video is about centripetal versus centrifugal forces for rotational motion. So let's start by imagining a ball on a string. And it is traveling this way. Sorry, let me make that a little bit better. It's traveling this way around the circle like this. Okay. And it has some tangential velocity. So for the moment, it doesn't matter whether we imagine this being sort of a vertical circle, like you were, spinning spinning a bucket of water, trying to keep the water from falling out, or whether you're spinning something over your head in more of a horizontal circle. It doesn't really matter, but I'm just going to view this as top down. So we're looking top down at this thing. So we know from earlier that at all times there is a centripetal acceleration directed towards the middle at all times, and that's what causes a curved path. And again, we looked at this vectorially just yesterday. So if there's an acceleration towards the center, there must be a force directed towards the center, F equals ma. You can't have accelerations without forces. And so this inward directed force is called centripetal force. So I'm just going to quickly jot that right down. Centripetal force is the force directed inward that causes the circular motion. In this case, it is the tension in the string. And sometimes it could be gravity if we're talking about the inward force keeping the Earth going around the sun. Right, so there's different examples of centripetal forces. So that is what centripetal force is. Now, imagine, and again, this is something you're going to have to imagine, that you actually have this ball on a string, maybe it's a tennis ball on a string, and you start to spin it around and around. The tension, again, the centripetal force directed inward is provided by the tension in the string that you're holding, but you're also going to feel an outward pulling, and I'm going to do this actually with something a little bit more difference in color. You're going to feel an outward pull. And in fact, that's what causes you, for example, if you just imagine that the rope is really slippery, that as you're spinning this thing around and around, the rope might slip through your fingers and then the object goes flying away, goes flying out. So it feels like there's an outward pull here. Let's just write down. There is an outward pull, and I'm putting quotes around pull for a moment here. There's an outward pull from the circle that feels like a force, emphasis on feels. But if you think about it logically, really what's happening is if you were to let's imagine that the ball is right here. If you were to let go right there, even though you feel a force outward, you feel this force outward, the ball is not going to fly this way. It will not fly outward. It's going to fly tangentially, right? So this outward pull that you're feeling is not really an outward force, because again, if it was an outward force, the object would just fly outward radially, which is this green path, but in reality, it's only going to fly off tangentially. Why will it fly off tangentially? Because this outward pull is not actually a real force. It's actually just the inertia of the object. This is Newton's first law. This is the object wants to continue moving in a path, or an object in motion will remain in motion in a straight line at a constant velocity. Okay, so the object was currently at this point right here moving to the right, and so it wants to continue moving to the right, and so it's sort of pulling on the rope, and you're providing the tension in the rope, which causes it to accelerate inward, meaning which causes it to turn. So you're providing the inward force. The object wants to continue going in a straight line, but it can't because of your inward force, in this case by the tension in the string. It feels like an outward force, but again, if you were to release the string, it's not going to fly outward. It's going to fly tangentially. One more time, because it's just simply inertia. So centrifugal force, and maybe we'll do, well, you know what, I'll just keep this, I'll go a little darker. Centrifugal force, I'll say oh, that's much nicer. Centrifugal force is a false force. Again, because it is simply Newton's third law. Excuse me, Newton's first law. Excuse me there. Remember, Newton's first law is also called the law of inertia. All right. So now here comes the interesting part. I'm going to jump down here. I'm going to redraw this ball in a string. Now here's where it gets a little interesting. Even though centrifugal force is a false force, it acts like a real force. Oops, sorry. It acts like a real force. And we will actually, this is the crazy part, we will actually calculate it as if it was a real force. So this is the part here. Now we're going to treat something, and I'll use my little arrows here. This is the... Again, it feels like it's an outward force. We know from the previous thing I talked about that it's not a real force. We know that there is an actual real life force going this way. And we know that the equation for centripetal force is m v sub t squared all over r, or mr omega squared, right? Because F is equal to ma, and this, you know, either this or this were your A sub c's, right? So ma. All right. Okay, so I'm going to continue off this. I'm going to continue this now with an emphasis on this idea right here, that we can calculate the centrifugal force as if it was a real force. So that is what I'm going to focus on right now. Again, I'm going to go back to my ball and a string. Very handy little demonstration tool. And let's imagine again that it's traveling around like this. I'm going to point out again that there is the centrifugal acceleration, centripetal acceleration pointed inward, and this fake force, centrifugal force pointed outward. All right, and let's make this a little bit bigger. So I'm going to start with the equation for the centripetal force, which is F sub c is equal to mr omega squared, and it, of course, doesn't really matter, mv sub t squared all over r, same thing. Now, here's where we got to think about what's happening with these forces. Now, we're spinning this ball around, make it a little bit more obvious here. As the ball travels around, notice that it is not getting any closer to the axis, and it is not getting any further away from the axis, right? It's traveling around the circular path, maintaining this distance r. If the centripetal, the blue one, if the centripetal force was the only force acting on this thing, then it would be radially accelerating inward, right? The path, and I'm just going to do this fairly lightly here. If it was the only force, you would notice that this thing would start to radially accelerate inward if the only force was inward. If the centrifugal force was the only force, it would be flying outward. But let's just say that they're both present, but the centrifugal force was slightly bigger. If the centrifugal force was slightly bigger, you would see this thing start to radially accelerate outward, right? Because there'd be a net force outward and not inward. And hi Marie, making a video. So the fact that this ball on a string is not accelerating radially inward, like the blue line, and the fact that it's not accelerating radially outward, please don't say anything embarrassing, honey, I am making a video. They're at the dentist right now. The fact that the ball is not accelerating radially inward or outward tells you that F sub c has to be equal to the centrifugal force. Remember, I'm calling this centrifugal force with quotes around the term. It's force. It's a fake force, but it acts like a force. What this allows us to do, and remember, this is real, this is fake, or not a true force. I mean, it's, but what it allows us to do is that we can calculate the magnitude of this centrifugal fake force because we know it's equal to a real force, which is centripetal force, and we already know the equation for centripetal force. So what it means is that the equation for centrifugal force is the same as the equation for centripetal force, which means it's going to be mr omega squared or mv sub t squared all over r. Again, it is a fake force, but through a little bit of sleight of hand and cleverness, and it's mathematically sound, we can calculate the magnitude of this centrifugal force by setting it equal to a real force, which is calculatable, whatever that word is. Again, this holds true because the outward force has to be equal to the inward force. The outward fake force has to be equal to the inward true force because the object is not radially accelerating inward or outward. Now, if we do an example where the object is accelerating inward or outward, then the statement's not true. They're not equal. But in this case, in most cases, they are. Okay. The next video will be a sample problem and showing how we use this idea.